Good morning, everybody. This video is going to be all about work, okay? Not like the work we do at home, but the work that has to do as far as energy is concerned. So let's remind ourselves of the equation. The equation for work is W equals FD or FD cosine theta, okay? So that W is the work. And remember that work can be measured in Newton meters or joules. Okay. F is our force, and that is measured in newtons. And D is our displacement. Okay, and that is measured in meters. Okay. So the reason we tack the cosine theta on there is because the force and the displacement must be parallel, or I'm going to say partially parallel in order to do work. So that theta, okay, is the angle between the force and the displacement. And the fact that we're using cosine allows us to take into account that parallel piece. So if I have a box that is being pulled across a surface, let's say a distance d, by a force F at an angle theta, okay, I want the part of the force that is parallel to that displacement. So I want this part of the force. Okay. I want that part of the force. So if I look, that side is the side adjacent to the angle, which means I need to use cosine because cosine goes with adjacent. So that's the main definition of force. The other work. The other definition of work that we have is this idea of the work energy theorem. So the work energy theorem states that any work that's done on a system is going to change the energy of a system. Okay? So if that work is done by an external force. Okay, so examples of external forces might be friction, it might be applied forces, and if we're not including the earth in our system, it might be forces due to gravity. Okay, so if that work is being done by an external force, we say that that delta E is really a change in E total. And it usually, or in this case, is always going to mean a change. I don't know why my pen isn't working. Change in kinetic energy. Okay, so we can set the work equal to the change in kinetic energy, which is really the final kinetic energy minus the initial kinetic energy. Okay. Now, one thing to be wary of here is a lot of people like to rewrite this equation as V final minus V initial squared. Okay. That is very, very wrong. Don't do that. Okay. The best way to simplify this equation is 1/2 m square the V final minus square the V initial. Okay. That's the only way to simplify this. You can't do V final minus V initial squared. Okay. If that work is done by an internal force, okay, so something like a box pushing a spring, or if Earth is in our system, it might be gravity. Okay, the work being done is going to either change the gravitational potential energy or the spring potential energy. But usually our total energy is not going to change. For the most part, the work questions that we're going to see are going to deal with external forces, okay, like friction or something like that. Okay. So now let's talk about direction, because with work it sort of matters, but not in the same way that it matters with vectors. Okay. So when we've talked about positive versus negative before, it's just meant direction. But with work and energy, positive versus negative actually means positive versus negative. So positive means adding energy, negative means taking away energy. So if we have an object being pulled by a force F over a distance D, in this case, the force and the distance are in the same direction, meaning they're both pulling in the same direction, or both going in the same direction. So the theta that we're dealing with is 0. Now, if we think about it, the cosine of 0 is a positive 1. So that means we have positive work done, so we are going to increase our energy. If we have an object that has a force acting on it backwards while it moves forwards, for example, a force of friction acting as it moves forward, well, if that's the case, then theta is 180 degrees, and the cosine of 180 degrees is negative 1, okay, which means we have negative work being done, so that's going to decrease our total energy. Now, let's say we have an object being lifted while also moving horizontally, okay? Or a force being applied vertically while also being moved horizontally. So for example, this might be the normal force. Okay? Here, the angle between the normal force and the distance is 90 degrees, and the cosine of 90 is 0. So that means the work being done by the normal force is 0 joules. Okay. And let's say that this first one was an applied force. So we could look at all the forces separately, or what we could do is just figure out what our net force is, and then we could figure out our total work done by that net force. And it makes it so that we don't have to take all those individual forces into account. So we might do something like an applied force minus a force of friction gives us our net force. And then we can use that equation, or that value for the net force, in the work equation. The last thing I want to talk about with work is the graphs that we might need to look at. Okay, so we have force and displacement graphs that we're going to look at for this situation. Okay, so we might have a graph, I don't know, that looks like that or something. Okay. So again, we got a TSA. Title is force versus distance. Slope is force over distance. Area is force times distance. So if it's not jumping out at you immediately, you can use units to help you figure it out. So Newton divided by meter, well, that's usually a spring constant. So maybe this slope might tell me information about a spring constant. And FD is Newton times meters. Oh, well, that's work, or change in energy. Okay. So the area between the graph and the axis is going to tell me about the work done, or the change in area. So there's really two sections of area for this graph. Okay, there's that blue section and then this larger red section. Okay, so we're going to say that whenever the force is positive, we're going to assume that our positive direction, or our object, is moving in the positive direction. Okay, so this whole area here is going to represent positive work, which means our energy is increasing. Okay, so during this time, the object is likely speeding up. Okay, even when the force is decreasing in this section here, the object's still speeding up. We're still applying a force, just less force. Then in this section here, because the force is negative, which means it's pointing in the opposite direction that the object is moving, the work done is going to be negative, which means that our energy is going to be decreasing. Okay, so this object is likely slowing down. My cats are doing an Indy 500 right now. Okay. Now, what we can do with that area is we can figure out information about the speed. So we can take, say, let's call this area 1. Okay, so I'll call that work 1. So we can take that area, or work 1, which looks like an area of a rectangle and an area of a triangle, and we can set that equal to the change in kinetic energy. Okay. So we can say work 1 is going to be KE final minus KE initial. If we're lucky, the initial velocity will be 0, but that's not always the case. Sometimes we do have an initial velocity. Okay. And we could use this to help us figure out what the final velocity of the object might be at that given time. Okay? And then we could do the same thing with the red area, or W2. That brings us to the end of everything that you need to know about work for review. More videos coming soon on the rest of energy.